Hello friends, welcome to Mu Lessons. In the previous few videos, we have seen about the network theorems and the most two important network theorems which are widely used in solving the circuits are the Thevenin's and Norton theorems. So I have decided to make several slides or a different video for both of this and describing some useful numericals so that the concept will be very clear for you. Now for this Thevenin theorem, consider the following, that is, we have two networks, network 1 and network 2, and they are somewhat, you can say, coupled networks. These are the 2 points A and B. Now for the purpose of discussion at this point, we consider that both networks are composed of resistors and independent voltage and current sources. Now suppose network 2 is detached from network 1 and we only focus temporarily on network 1. So this acts as an open circuit and we have two terminals, that is A and B. Now network 1 can be as complicated as in structure. This whole part, network 1 can be as complicated structure. We can imagine it can have 45 meshes, 387 resistors. These are some just examples. It can also have such type of quantities, meshes, resistors, voltage sources, lot many things. Now place a voltmeter across the terminal A and B and read the voltage. We call this as open circuit voltage. Now no matter how complicated this network 1 is, we can read one voltage. So by using a voltmeter you can obviously read the voltage across the terminals A and B. Now it is either positive at A with respect to B or negative at A with respect to B. So we call this voltage at OS, VOS. Or you can say VTH or Thevenin. Now we deactivate all the sources of network 1. This is procedure wise I am explaining how this Thevenin's theorem work actually. Now we deactivate all the sources of network 1. To deactivate all the sources of network 1 or to deactivate the voltage source, we remove the source and replace with a short circuit. Remember, all the voltage sources, or every time you replace a voltage source, it is to be replaced with a short circuit. And to deactivate a current source, we remove the source and it can be replaced by an open circuit. So current source has to be replaced, or a current source has to be deactivated by a open circuit, and a voltage source has to be deactivated by a short circuit. This is to be remembered. Now consider the following circuit. You can see there are several loops, some current sources, some voltage sources. This is a typical circuit which is independent source. Now how do we deactivate the sources of this type of circuit? This is the first question. When the sources are deactivated, the circuit appears as like this. You can see all the sources, it may be current source or voltage source, all has been removed. Now the main point to remember is the current source. Wherever you see this open circuit, that means the current source has been removed, and in these parts, that is the short circuited part, voltage source has removed. So voltage source is replaced by short circuit and current source is replaced by an open circuit. This is very important. Now place an ohmmeter across the AB terminal and read the resistance. Suppose if R1, R2 and R4 are given as equal resistance, that is 20, and R3 is 10, then the emitter meter will read 10 ohm. You can find the equivalent of all the four resistances. These two in series, in parallel, then series. So we call the ohmmeter reading under this condition as R Thevenin or RTH. Therefore, the important results are that we can replace the network 1 with the help of a following network. So this is the whole system of network 1. That means a whole network. Suppose in the previous slides I have already told that it can consist of 39 current sources, 100 of voltage sources and many meshes, thousands of meshes. So that can be replaced by a simple network with a voltage source VTH, that is Thevenin voltage, and with the current source, the equivalent resistance, resistance, that is RTH. So that is the equivalent Thevenin equivalent circuit. Now we can now tie or reconnect again the network 2 back to this terminal. Now after working with whole of this part of network 1, we again connect network 2. So this time it becomes quite simpler than the previous case. We can now make any calculations we desire within network 2 and they will give the same results as we have found when network 1 was connected. So these two cases, all the readings, all the values are same. It follows that we can replace also network 2 with a Thevenin voltage and a Thevenin resistance. Corresponding Thevenin voltage and Thevenin resistance for network 2 as well as network 1 can be used simultaneously. So if we use it simultaneously, you can see such a picture, and in this case, while dealing with such a case, the complexity decreases and it really decreases to lot. That means in this case we have two resistances in series, two resistances in parallel and two voltage sources in parallel. Now you can see this question is an example. You have to find Vx, that is a voltage across a 2 ohm resistance by first finding Vth, Rth to the left of AB. Now it has been said that we have to find the Rth and Vth from this part. So first remove everything to the right, that is of AB. You can remove everything from this part. So it looks somewhat like this. Now from this you can calculate VAB, that is a voltage across AB. The voltage across AB is given as 30 into 6 by 6 plus 12. This is simple, very simple to calculate. Just by voltage division rule you can calculate it. Note there is no current flowing through 4 ohm resistance. This is very important. There is no current flowing through 4 ohm resistance, and hence because AB is open, so there is no use of this 4 ohm. Thus there can be no voltage also across this resistor, no drop across this 4 ohm resistance. So by using simple voltage divider rule or simple by applying Ohm's law, you can get VAB. Clear? Now we can deactivate the source to the left of AB and find the resistance seen looking at these terminals. Now as there was a voltage source, it has been replaced with a short circuit, and we have three types of resistances. So simply when you look at from this part, these two resistance 6 and 12 are in parallel, then 4 in series. So the net equivalent resistance, that is RTH, will be 8 ohms. I am moving very slowly so that you can understand each step, so that there will be no problem in further studies of Thevenin and Norton. These two theorems are very much useful for electrical students and as well as for other students in the first and second sem. Now after having found the Thevenin's equivalent, we can connect or we can reconnect the load in order to find the Vx. Now for the previous diagram or the question, we have replaced it with Vth and Rth, and now we have connected a load resistance to a 2 ohm resistance, and now we have to find the voltage across this 2 ohm resistance. So in this part it becomes very easy. So Vx is the voltage across this, will be net current flowing through this 2 ohm resistance into 2. So the net current flowing through this 2 ohm resistance will be net voltage 10 by 2 plus 8 into 2, and that comes out to be 2 volt. So you have seen how easily it can be solved using Thevenin's theorem. In some cases it may look tedious to find RTH by reducing the resistive network with the source deactivated. Now consider the following. In this part you can see Vth, Rth given with Is current flowing in this part. So the most complicated part comes to find the RTH by reducing the resistive networks with the source deactivated. So in this case we see RTH will be Vth by Iss, that is a current flowing through this. As Iss is the current given, short circuit current flowing through the circuit, so net Thevenin resistance RTH will be VTH by ISS. Now for the circuit, this is the same circuit which you have seen previously. Now the task is now to find ISS in this case. So one way to do is to replace the circuit to the left of the CD. This is the terminal CD with a Thevenin voltage and a Thevenin resistance. Then we can proceed as we have seen previously. So let us see. Just keep a look on how this has changed. We have to replace the circuit to the left of the CD with the Thevenin voltage and the Thevenin resistance. So this part, now applying the Thevenin's theorem to the left of the part terminal CD and reconnecting it to the load again gives such a circuit diagram. This is the Thevenin voltage, Thevenin resistance. Now what happens in this case, we have to calculate the RTH, and RTH will be VTH by IS. So what is IS? IS is the net voltage by net current flowing in this whole circuit. Net voltage means 10 by 8 and VTH is given as 10. So RTH will be 10 by 8 and that comes up to be 8 ohm. So RTH for this case is 8 ohm. Now for the circuit below, we have to find VAB by first finding the Thevenin circuit to the left of the terminal AB. Now it has been given that we have to find from this left terminal AB, we first find VTH with 17 ohm removed. Now we have to remove first of all the terminal which has to be found out, that has to be considered as load terminal or the load resistance or the load impedance. So we need to remove it from that part and then we have to start solving it. Now first 17 ohm is removed, then next we have to find the RTH by looking to the terminal AB with all the sources deactivated. Remember how to deactivate the source. Voltage source can be deactivated by a short circuit and current source can be deactivated by open circuit. So you can see 17 ohm resistance has been removed. So AB behaves as a open circuit. So VOS equals to VAB equals to VTH, and this VTH can be found out by the net voltage, that is 1.5 ampere into 10 current, net current flowing through this 10 ohm plus 20 into 20 by 20 plus 5. That means you have to calculate the net voltage across AB. You have to see it, please look it carefully. The voltage across AB is the voltage across 20 plus voltage across this 10. Clear? Once again I repeat, the voltage across this open circuit AB is the voltage across 20 and the voltage across this 10 ohm. So how to get the voltage across this 20? Simple, by voltage division rule. 20 into 20 by 20 plus 5. And how to get the voltage across this 10 ohm resistance? Simply V equals to IR 1.5 into 10. So we get the net voltage is equals to 31 volt, and that is the VTH. Now for finding RTH, you are quite aware of how to calculate this RTH. 5 and 20 are in parallel and it is in series with 10 ohm. So RTH equals to 14 ohm. So finally we get the whole circuit as VTH equals 31 ohm, RTH equals to 14 ohm, and we have the load resistance, it is 17 ohm. So in this way we can easily find out VAB came up to be for 17 volt. So Thevenin's theorem are very useful for solving such complex circuits, and they make our tedious tasks also very easy. Now working with a mix of independent and dependent sources. In this part we have some independent sources and some dependent sources like 6IS. So find the voltage across the 100 ohm load resistance by finding the Thevenin circuit to the left of the terminal AB. We have been advised first to find the Thevenin circuit from this terminal left of the terminal AB. So we remove this 100 ohm resistance and we look into this from this open circuit part, that is AB. So voltage across AB is equals to VTH. Now as there is one dependent source and one independent source, we have to use it very carefully. Now by applying KVL in this part, 86 plus 80 IS plus 6S equals to 0. So IS comes up to be 1 ampere. Similarly VAB will be a voltage across this whole branch, across this 40 plus voltage across this part. Basically there will be no voltage across this 40 because it has been open circuited. So the only voltage will be VAB is equals to 6 into IS plus 30 into IS, and that is comes to be 36 volt. Now to find the RTH, we deactivate all the independent sources but retain the dependent sources. So the independent sources was a voltage source which was replaced by short circuit, and we keep the dependent source. We cannot find RTH of the above circuit as it stands. We must apply either a voltage or current source at the load and calculate the ratio of this voltage to the current to find this RTH. So in this case it is very complicated to find the value of RTH, but we will still proceed. Now we will around the loop at the left we write the following equation, that is 50 IS plus 30 IS plus 1 plus 6 IS is equals to 0, from which we get IS equals to minus 15 by 43 ampere. Now note what was said previously. We cannot find this RTH of the above circuit, so we must apply either a voltage or current source at the load and calculate the ratio of this voltage to the current to find the RTH. So we have applied a voltage or current source at the load, that is of 1 ampere, and hence we have calculated by taking this particular loop 50 IS plus 30 into IS plus 1 plus 6 IS. From that IS came to be minus 15 by 43 ampere. Now using the outer loop, going in clockwise direction, again using the drops in these voltages, we can get this particular value 50 into minus 15 by 43 IA, means the outer loop, minus 40 into plus V, that is the voltage across this particular branch. So V comes up to be 57.4 volts. So RTH will be V by I, that is I is taken as 1 ampere, so V RTH equals to 57.4 ohms. This was little critical, so I will tell you just one more time. Now in this part we have to calculate RTH, so we will replace it in such a way that we can apply either a voltage or current source at the load part, and we have to calculate the ratio of this voltage to the current to find the RTH. Clear? Now for that we have replaced it with 1 ampere current source, then we have taken two loop equations, that is the left side loop and the outer loop, and we got RTH equals to the ratio between the voltage and current, that is V by I, 57.4 ohms. Similarly there are some examples like you can see here. Sorry, this is continuing. Now it has been replaced with VTH and RTH, and similarly the voltage across 100 ohm will be 36 into 100 by 57.4 plus 100, and the voltage across this 100 ohm will be 22.9 volts. Now here is another question. This is having a current source and a voltage source. Now I would request you to try this question first, then in the next video we will be looking at the solution part of this particular question. So hope you like this video, and the more you will go through the books and numericals, and it will be better for you. Thank you.